As mentioned in the two previous videos, the goal has been to find a low-cost way to charge up the solar battery bank when the solar panels are not getting enough sunshine. Pictured here is the latest configuration that I found works reliably and avoids the three major issues that I encountered with previous circuit designs: short circuit conditions, reverse current flow from the battery, and maintaining a floating voltage source. The Victron isolated DC-DC converter, pictured here in dark blue, provides both short circuit protection and a floating voltage source. The blocking diode, pictured at the bottom, prevents reverse current flow from the battery. Note that the PTC from previous videos has been removed and replaced with a simple 15 amp blue blade fuse. Although there is already a 15 amp glass fuse in the 12 volt plug itself, the new 15 amp fuse can be a fast blow fuse or could be replaced with a lower value fuse if future testing shows that can be done. At the end of this video, I will discuss some additional improvements for further testing and give a summary of the cost of parts. This is a screenshot from my laptop, which displays data that it collects via a serial cable from the charge controller. Without going into detail on all of the items presented, here are a few of them. The top line of data shows the voltage and current being drawn from the solar panel. But in this case, it's actually the voltage and current being drawn from the Victron DC to DC converter, because I unplugged the solar panel from the charge controller and plugged in the output from the Victron converter instead. The voltage reading is 24.2 volts, which is exactly the open circuit voltage that is provided by the Victron DC to DC converter. In the second line of data, the reading of 12.9 volts shows the voltage at the battery terminals, and the battery current of 0 shows that no current is being sent to the battery by the charge controller. The right-hand box at the end of the second line shows the state of the controller is idle, which means it is not currently charging the battery bank. And last, the middle box on the third line shows that the battery is 89% charged, where the acronym SOC refers to the state of charge. After a few seconds, the charge controller will begin drawing power from the DC current source, and the charging state will change. This screenshot was taken just after the charge controller started to draw power from the DC to DC converter and started to charge the battery bank. Note in the first line of data that 18.1 volts at 5.58 amps is being drawn from the DC to DC converter, and from the second line that a current of 7.96 amps at 12.8 volts is being sent to the battery bank. The right-hand box at the end of the second line, the charging state has changed from idle to MPPT. Without going into detail on how the charging proceeds, as the battery bank gets close to fully charged, it will switch from a more or less constant current mode to a more or less constant voltage mode. This last screenshot was taken while the controller switched from constant current to constant voltage mode. Note that the battery voltage has gone up while the battery current has gone down. Here is a photo showing what current is actually being drawn on the input side of the Victron DC to DC converter, because the previous screenshots only show the output side of the Victron, which is what the charge controller sees. It does not see the input side. Note that the current is just below 15 amps, the maximum allowed for the van's 12-volt DC outlet. One issue that I encountered with this latest round of testing was excessive heat at the 12-volt plug itself. So it's important to get a 12-volt DC plug that can normally handle currents up to 15 amps without excessive heat building up in the plug. Since the input voltage is 12.67 volts at the van's 12-volt DC outlet, it's nominally 12 volts. It's actually measured at 12.67 volts. And the measured input current, shown in this photo, is 10.6 amps. The power drawn from the starting battery would be 134.3 watts. Since the output from the Victron is nominally 120 watts, we get 120 over 134.3, which is about 89% efficiency, which is very close to the advertised efficiency of 88% for the Victron. This is a summary of the costs for all the parts for this circuit. I am satisfied with this circuit and have no immediate plans to change it. I may at some point use a second Victron DC to DC converter in parallel with this circuit. That would give me effectively the same charging capacity as the Renogy 20 amp DC to DC battery charger. That would be a fair comparison with the Renogy 20 amp DC to DC charger, because I can get two Victron isolated DC to DC converters for slightly less than the cost of the Renogy. And as you can see, the wiring requirements are very simple and nowhere near the $300 cost of cabling needed by the Renogy battery charger. Not to mention possibly having to drill holes in the frame to pass the cables. This, of course, assumes that you have two 12-volt DC outlets available that are on separate circuits, allowing you to use two Victron DC to DC converters simultaneously. That is the case with my van, but not all vans have two 12-volt DC outlets on separate 15 amp circuits. I will post more in the future as I gain experience with this low-cost method of charging my battery bank, but for now, I am satisfied that the major issues have been addressed. Your comments and suggestions are invited, and thanks for watching.